just need a bit more. Okay, one more example of a difference quotient. I thought I'd give you one more taste of something else. Let's try this guy. Anybody get this challenge problem I offered to a couple people? What's the derivative if f of x is a polynomial function in general?
I don't think I got that one from you.
No? Oh.
Well, I'm sure you could solve it, but...
Well, I'm going to do it for you. It's a big
you.
example, but I want to see if someone could do it without me. I didn't offer it to you, did I?
No.
Yeah, so this is a challenge. If you can find the derivative of this function for me in general by doing the longhand
Do you get a point extra credit on the
Oh,
test?
you do.
Just one.
I'll offer 2 points extra credit on the test. Sure.
Okay, I'm writing it down.
Which,
So what, we just have to write it on the test and show you that we have it?
no, you just have to turn it into me. Explain it to me. Okay, anyway, let's do this guy. So we eventually want to find the slope of the tangent there, and let's just go ahead and find the tangent line. If we've already found the slope of it, there's no point in just not finishing. Okay, so let's find the derivative. Now when we do this, we're going to find the derivative function in general. You can find the derivative at a specific point. That's what your calculator can do, right? Like if you plug it in, I showed you yesterday on the screen how to just find the derivative at a specific point, but it didn't give you the actual function, which is everywhere. And how does that function relate to the original f, and what do they look like together? We're going to start exploring that a little bit. Okay, well, let's just do the limit. So fx plus h minus fx.
How's that me?
Okay. So I'm going to go 4 over x plus h minus 4 over x all over h. Yeah. I've done this tons and tons of times. So what do you guys think I should do? I've done problems exactly
Flip
like
the
this
h
before.
and then find a common denominator.
Common
Wait,
denominator
there's
before
two
you
things.
flip the
Well, you
h.
could do
Does
either
it matter
or.
which one you do first? I hear I gotta put that h up there
I
somehow.
would
doesn't
put the
matter.
h up there after, because it'll be easier.
That's fine. Can you do them at the same time?
No, you can't. It's not possible.
Yeah, you can.
Yeah, you
Watch.
can right here.
I know you can, it's just too much
Okay.
math in one step.
4x
minus 4x minus
4x plus h. Yeah, you're fine. You're taking it even
Over
further. Very nice.
hx, x plus h.
And then this guy goes on the top or on the bottom? Why does it go on the bottom again?
Because it's like h over 1.
This is an integer or fraction. Think of it like that. It's not a fraction. If it was a fraction, we'd flip and it would go on top.
It's just
It's not. It's not a fraction, so it goes on the bottom. It's like times 1/2. If you have over 2, that's the same thing as times 1/2, right?
So it doesn't flip,
No, no flipping.
it just goes onto the
It
bottom.
just goes on the bottom.
Oh, Caitlin, we messed up on 20. Cassie, we messed
Do you
up
see
on
the
20.
difference though, Austin? It's because of this. If you have a fourth divided by 2, what's a fourth divided by 2? Isn't it an eighth?
yeah.
Well, think about it. If you flip that up, you get 2/4, which is half.
Oh.
That's not right.
That's not how I meant flip it up. Like if you put 2 over 1, if it's like 2 over 1, then you flip it like this, like, oh god.
Don't make this so hard. Just leave 1/4.
Okay, well, Cassie, we did it.
Dividing by a half means you put the 2 on the bottom, so it's
Yeah.
1/8.
Yeah.
Now, if this thing is not just 2, if it's 1/7, then you flip, and the 7 goes on top, right? It's a big thing. It's going to keep coming
Alberto
up.
taught me the over one thing.
Stuff, it goes back to people who are good at calculus are good at algebra. If you're good at algebra, you're good at calculus.
So you get the same thing.
Okay, then we see that our normal stuff cancels. Notice, if you don't take one more step here, I think it's dangerous. I bet a lot of us would make mistakes because we might write like -1 or even worse, with just +1 there. What's really going to be left when we cancel those h's? A -4 is left up there, right? So be careful. I've I've got a -4 left up there when I cancel those h's.
Okay.
Remember, Austin, I keep telling you, absorption time. We'll get it. Now the question is, can we do our limit now? Because I don't see much else we can do with that. Try it. You can always try it at any step, right? It's your choice. Key was, this h was screwing us up, so it was still there, it was still there. We finally got rid of it, which means we can probably use our limit safely now,
Yeah,
right?
you can do it.
So when I do that, I get -4 over
X
Squared.
x squared. I believe that is the derivative of 4 over x.
So then you substitute that into like,
So now the question is what they ask me to do with it.
that's the,
Find the slope of the
but
tangent
isn't
line.
that this,
That's a function which represents the derivative of that function. If I want the slope at a specific spot, I go f prime of that spot, which was 4, 1, so x is 4. So that's the slope of a tangent line right there. Whenever you see this, you can think of it as the derivative at 4, or you can think of it as the slope of the tangent line of f
okay.
at that spot. Okay? There's different ways to think about it. So I'm going to go -4 over 4 squared, which is just -1/4, isn't it?
Okay, so that's the last step.
Yeah. So we did what they said. Let's find the tangent line though, just real quick.
Yeah, I see if I can do this. This shouldn't be hard.
Austin, all you have to do is find the derivative.
No,
No, it's if I can slope.
for you guys, I don't think this is going to be hard.
But on like,
X minus 4, so y is -1/4 x. So I've got positive 2. Where did I get 2?
Yeah, the one
That was
back
the
up.
1, got that one, and you get 2. Cool? Alright. So I think I've shown you enough examples to handle all yours. Yes, I gave you a couple harder ones. Don't give up on them. Let's look at one other thing that's in here. Big important thing.
I think that's what you want.
So let's just talk about how this derivative works again, because I'm betting we're still a little bit fuzzy. So let's say we have a function. I'm just going to draw some piece of a function, okay? That function looks continuous in this region, at least in this neighborhood, okay? So I'm going to say, let's try to find the derivative of that function at this guy, at x. The way we did that before, theoretically, is didn't we go out a certain distance h this way?
Yeah.
So we said, okay, go out a certain distance h that way. And then h is coming, as you take the limit as h approaches 0, isn't it going this way? And h is becoming smaller and smaller and smaller and smaller. And up here, what's going on is you've got a secant line that's getting
Closer and closer.
closer and closer and closer to becoming the tangent line. Right? So being able to picture this is really important. Pretty important concept. Being able to see, oh, that's a secant line. It's not perfect to the tangent line right here. But when we shrink h, it goes, and eventually when h is perfectly 0, we get the tangent line, right? There's another way to come up with the derivative. In fact, there's more than one other way. I thought it'd be interesting to show it to you. So that's a one-sided version of the derivative. You can also take the limit as h approaches 0. And this is kind of more the way your calculator works when it does derivatives. That's why another reason I thought I'd show it to you. But just to prove that this isn't the only way to think. You can also go from both sides.
From left and right.
So you can go like, what is this point right here? Can somebody help me?
Could have did whatever you wanted to do.
X plus 8.
According to my labels, it's x plus h, isn't it? Somebody else wants this point then.
X minus.
X minus h, thank you, Austin. Okay. So then if we think about the slope of this secant line, see this is a different version. Before we went out one way. Now we're going out both ways, and now the secant line is between x minus h and x plus h, right? So let's find the slope of that secant line, because isn't that what we put in front of this to find the tangent line? We take the limit of the secant line. So let's find the slope. This is not a hard concept. This is just slope. Don't make it too hard. So we have like y2 minus, let's just write it down, y2 minus y1, x2 minus x1, just to make it easy to think about. I would never do that, but to make it easy for you guys. What's y2 if I'm thinking that secant line?
X plus H.
That's a y value? You're close. That's
It's
the x
f
value.
of x plus h.
It's f of x plus h. It's this, right? That's f of x plus h. So it's f of x plus h minus, what's y1?
F of x minus h.
F of x minus h. Am I starting to understand how this works a little bit better? And then what's x1? Or, excuse me, x2. It's x plus h minus x1. And notice I had to put some parentheses on there, didn't I? Okay, so now you simplify that a bit. Can I simplify much on top? I don't think so. Those are like stuck inside there. So I've still got a limit. I've got an x plus h minus an x minus h. What do I have on the bottom?
2h.
What happens when you distribute that minus? You get minus x and plus h. What happens? Gone. And how many h's do we have? There's two positive ones, aren't there? So that's 2h. There is an alternative version of the derivative.
So
The
there.
version that we did, the simpler version, which we'll always use in this class, is we were thinking about decreasing h and coming just this way. That's a one-sided version of the derivative. This is a, you start on both sides and work your way back.
So then that's it. That's the answer.
Yeah, that is like just as good for finding derivatives. You could use it to prove the derivative formulas that we're going to be using this year. I don't think it was formulas, I guess, just to prove the shortcuts. Okay, you could use it just as well. And in fact, this is used by software a lot more often because it turns out for software it's easier to go out both ways. You get a lot more accurate answers and stuff if you go out both ways instead of going out just one way. Interesting way to think about it, though. Did that solid up what we're doing a little bit more, Austin? Yeah, I think it did. Hope so. Okay, something else. So there are a couple questions which take the derivative a little bit further, besides just calculating some with the limits. So let's talk about differentiability.
That's a weird.
So we had this concept of continuity being continuous or not, right? There's a very similar concept called being differentiable or not, and it comes up in all kinds of advanced theorems. It's really important. Continuous is just as important. Let's see how they like interact with each other a little bit. What is differentiability then, okay? Let's look at some graphs.
Differential, there's no L there.
It means can you make the derivative or not, right? Does that make sense? Differentiability means can you make the derivative or not? Is it available? So let me give you a couple examples. So 3 graphs. That's the marker is dying.
Estimating on that one, or are they touching on the middle one?
This is touching, yeah.
Okay.
Good question. Okay. So, this is going to illustrate what differentiable means. Can you guys help me with just building these functions? Let's use a little pre-calculus here. What is this? Or what might this be?
The absolute value.
Absolute value of
X squared.
2.
Okay.
Give
What
up
do I
on
mean?
it.
it's always you guys. You guys give me bad luck. Blaming you guys.
For the dry race marker, the fact
Or
that
it's
you
the end
missed.
of the day.
No. Blaming you guys. This one? I've never drawn this one in this kind of exaggerated form before, so you guys might not
Is it
recognize it.
X cubed?
Close though.
10.
It's not x cubed. X cubed looks like this. Looks like a tangent.
Close.
Really excited.
It's the inverse. It's close. Square root of x?
Cubed root.
Huh? Yeah.
It's cube root of x. Thank you, Kyle. You helped us out there.
God, you're just so smart to me.
Okay. This one, we haven't really seen these much in pre-calc. We could have studied them. That is has like a square root of something that's squared in here, blah, 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 blah. I don't know. We didn't study those, but whatever. Okay? These are three different features. This graph is differentiable everywhere except where do you think it might not be differentiable? Is it continuous everywhere? Let's think about it.
Yeah.
Let's talk about the continuity and differentiability. This is F, G, H, making up names. So F is continuous?
Yeah.
Any places it's not continuous? I think we're good. It's continuous everywhere. Let's write negative infinity to infinity. Something like that, right? You could say everywhere, whatever. Is it differentiable everywhere? Can you take the derivative everywhere? Think about trying, what is the derivative? It's a tangent line. That's one way to think about it. Can you form a tangent line here?
Yeah.
How about there? Does the tangent line work?
Yeah.
It's that line, right? How about here? Tangent line?
That line.
Still that line.
So
Here?
the only place the derivative
Here?
works
No,
is
Wait,
that
why
to
is it
be
that?
a
Oh, okay.
tangent line throughout
Here?
the entire
Those
graph.
are all going to be the same tangent line, right? But what about here?
That's the only difference.
Well, there's still
Is the tangent line,
Isn't
you
it-
guys tell me, is it like this?
Is it x equals 0?
Couldn't it just be straight up and down?
You're
How about like
comparing
that?
to
One,
zero?
so it's straight up.
No, it's
Maybe
straight,
this?
the horizontal.
Yeah.
I have a question.
Isn't it the x
Couldn't
axis?
couldn't
Is there
it be
any way
straight
for
up
us
and
to
down?
decide which one of those it
So there
is?
could be
Straight up and
several
down.
tangent
Straight up and down.
Yeah. Is there any tangent, but how do you define tangent line? Like at a corner, I don't think the concept of a tangent line works anymore.
There's just too many possible.
Yeah, exactly, like you can't decide. It's like 0 over 0. 0 over 0 is indeterminate, you can't decide. Well there, you can't decide which one the tangent line is.
Why at those points is it that? Why is the tangent line that line? Like, I don't
Because
know.
if you make a tangent to the curve here,
Yeah.
Still.
you just
Make
touch,
a tangent line,
it's gonna have to
there's
be
no
like
way
that,
to
right?
bounce off of it. It's a line.
That's why on those problems that you
Yeah,
started
or-
yesterday, Austin,
touch.
remember the problems you had yesterday that were the beginning, and Caitlin said, oh, it's just a line, so the tangent line is it.
Yeah.
Okay.
If it's a line, the tangent line is it. There's no other way to do it. Because you can't make a tangent line like that, right? Or like that. It's just that.
Okay.
Don't think about it too hard. Okay. So this guy we can't decide. That means it's not differentiable there. You just can't find the derivative. It's impossible. It doesn't exist. If you try to with the limits, it's going to fail every time, no matter what. So f prime, well, let's just say it like this. F is not differentiable. Everywhere?
No, at -2.
At -2. That's key. Everywhere else.
+2, sorry.
Positive.
Could you just
Trick
say
me.
f of 2 is not differentiable?
Don't you make a tangent line just straight up?
F
Yeah, I
prime
guess. That'd be a little
2.
sloppy. I don't know.
You
It's not
want to
per-
say
that's
f
not
prime of
technically
2
right.
does not exist.
You can say f prime of 2 does not exist.
Oh, you
Exactly.
can cross it, just touch that.
I like that. That is true for sure. Good thinking. Okay, good stuff. Where's that issue going to happen on this graph? Is it continuous everywhere?
Yeah.
I'm trying to get at a theorem we're going to be doing here, right? So is G continuous? I think it's continuous everywhere. There's no issues with the limits or any of that stuff we learned about continuity. So G is continuous everywhere too. But when you try to take the tangent line, we're good, we're good, we're good, we're good, we're good. What happens once you get down in there? I don't know. How to find the tangent line?
At some point C where
Yeah, wherever this is. So G is not
Then how could you like right there?
differentiable. Is it continuous at that point?
Something else.
Yeah.
Yes, it is. Okay, that's key. It is continuous at that point. This point is called a cusp.
so at the cusp it's not differentiable.
At the cusp, it's continuous, but it's not differentiable. So G is not differentiable at the cusp. So we didn't really see too much in pre-calc with cusps, but we could have. It's just I chose not to. Okay. So we are not differentiable ever at a corner. We are not differentiable ever at a cusp. What else do you think you're not differentiable at?
The origin.
Well, where that's placed.
Where here, the origin. You guys are saying which x value? X equals 0. Why? This one seems a little weirder. This doesn't happen very often, by the way, but
Because either way you're going to eventually go through.
can you do a tangent line here?
No.
I think I can. I think it's a little bit different reason this isn't differentiable. I think I can write the tangent line down, but what's the slope of that tangent line?
Oh, it's a vertical, so it doesn't.
It's
Can't have
vertical,
it.
so the slope is
Non-existent.
undefined. The slope doesn't exist, so that means that the derivative
Yeah.
doesn't exist. It's a little bit different concept there, but it's the same thing. It's still not going to be differentiable there. Are we okay with that? Okay, so this guy's continuous everywhere, but he's not differentiable. So what should we call this? So we've got cusps, we've got corners, not differentiable there. What is this? If that happens, what should we call that?
It's a vertical.
It's a
asymptote
vertical
no, vertical tangent.
tangent line. If we have a vertical tangent line at that spot we're checking, it's not differentiable. Okay. So we talked about continuity and differentiability on each one of these, okay? So you guys tell me. I think I'm going to have you write. This is a very, very widely used theorem. We'll use it this year. Pretty simple. You guys see if you can guess what it means. Guess what it is. I bet we can after going through that. So the theorem involves differentiable and continuous. It's not an if and only if. In other words, you can't say if this, then this, and backwards too. It only works one way.
So it's just
So I'm going to let you fill in the blanks. Some theorems go back and forth. Those are the best ones. They're the strongest ones. Some of them don't, unfortunately. So I'm going to say if f's a function, is differentiable. Oh, crap. I already screwed it up.
Oh, okay.
I'm gonna leave that there.
Just leave the differential.
That's fine. I missed. I got too excited. Then f is also so disappointed. I have to make a whole new video.
It's also continuous.
Yep.
So if it's differentiable, did you guys look at those three examples I gave you? If it's differentiable at a point, is it going to be continuous there?
No.
Like, look at even the problems. Like, everywhere else, it was differentiable and continuous, right? Can you go backwards, the question is?
No, you cannot, because
Differentiable.
you
Because
had
why?
those examples where the cusp, it was continuous, but it was not differentiable.
Exactly. So if you try to go backwards, and you will be so tempted to try to go backwards. I asked you some like true-false questions about it, number one. But on problems that actually exist in the real world, it's so tempting to do this. It's so tempting to say, okay, I have a continuous function g of x, and I need it to be differentiable to do something to it, you know what I mean? And you're just like, well, it was continuous, so it's going to be differentiable, I'm going to be all right.
You can't
And you're
be
thinking, well,
confident.
it's continuous, that means it looks something like that, right? So, of course, that's going to be differentiable. What's going to be the problem? I can find tangent lines everywhere there. But then you forget, well, maybe it does that. It's still continuous, but I don't think I'm going to be able to do what I need to do if I need it to be differentiable right there. Okay? So you can't say that it's also differentiable. So if I have a continuous function g of x, then
it might be differential.
Exactly, I like that. It might be differentiable. And when I talk about continuity and differentiability, can I just say that without talking about where? I really can't, right? So it might be differentiable where I need it to be. But I don't know solely based on that. Clear? We're done.
Alright.